Land Mapping Project.
All right. So thank you, Jody. I'm Chris Beal. I work for the Superior National Forest on the Kentland Ranger District. I'm a wildlife biologist, and I've been working on this project as a tool set to address some of the data needs and the data concerns for all lands project planning. And so these are a lot of my close collaborators who've been working together on this for a while now, with the Nature Conservancy, Mark White, Jim Manolis, and Andrea Brandon, and also Mark Nelson with FIA. But this is just a small subset of all the collaborators and people that I'm working with for this project, because as you'll see, it's kind of an all hands-on deck initiative. So, and the other thing I'll add is if you were at the early session, a lot of the questions that came up had to do with how we look at the landscape, like specifically the question about the private landowner, like how do we come to a private landowner and make the case in the middle of some sort of block of other agencies or other initiatives that we're trying to make in this landscape? How do we come and present them with the information that's like, look, this treatment here that we could propose would help this larger mature patch or this wildlife habitat that we're trying to build here, or be part of a larger community. And I think the data piece of this that we're consolidating here could be a big part of that. So the all lands approach, for my familiarity with it, it really started with our Forest Service Chief, former Forest Service Chief Tom Tidwell in 2010. And this is a statement from a letter he sent out then. Restoration is predicated on partnerships. The effects of climate change cross borders and boundaries. No single one of us can succeed alone. Last year, we offered a broad vision for an all-lands approach to sustaining and restoring the nation's forests. That means using all USDA resources and authorities in collaboration with NRCS to sustain the entire matrix of federal, state, tribal, county, municipal, and private forests, which kind of summarizes the all lands approach in my mind. So why is all lands management difficult? So each land management agency is comfortable within its own silo, using its own data and processes to describe the existing condition, come up with management priorities, and make those treatments using the spatially explicit tools in their toolbox, mostly GIS layers, a lot of the time, stand inventory. But what about landscapes with multiple ownerships? That's the all lands question. So here's one reason why it's difficult. Using multiple stand inventory databases, if you've had to do management, you bring in 10 different layers, you're trying to switch between them. It's actually really hard to carry that forward into a comprehensive description of landscape that everyone can agree upon. Each stand inventory data set presents its unique idiosyncrasies, cover definitions don't match, there may be different upkeep schedules, and not to mention the alignment issues, because these databases weren't sketched with any idea that they need to be coincident or part of a seamless landscape. So here's one example. This is just 3 layers brought in. So you bring in ownership, and you bring in the black is one stand inventory data set. The state might be here in the red chalk lines. And this is all the data that you need as a resource specialist to make decisions. But it's a disaster to try and figure out. You basically just go right into your own silo, what you're comfortable with, and you ignore the other stuff because you can't easily match or crosswalk between all these different data sets. And when we talk about managing for wildlife habitat, we're talking about needing enormously different data sets with their own definitions and needing to layer those all together and to fight between all those distinctions and idiosyncrasies to come up with just a description of what condition the project area is in. So then you say, okay, I'm not going to deal with all these inventory data sets, I'll stick with mine, but then I'll bring in remotely sensed cover data sets. These are wonderful, but like the National Land Cover Database, land fire definitions, or our LiDAR data, they're not up to date, they may be from mismatched time periods, or they're not generalized at an appropriate scale. They may be too much data. If you're looking at 30-meter pixels, maybe that's more than you need, it's too messy. or they're too broad to be overly useful. So in discussions at forums like this, at a lot of the GIS talks that the DNR has hosted and NRI, and a lot of meetings, what often comes to the surface about a priority need is a more comprehensive look at our existing data and leveraging that data into something that's more usable for all lands project planning. So this is the project premise, that given our existing data, we are not leveraging all that's out there effectively to solve the all lands management problem. So we have a wealth of existing data sets that taken together could address our all lands project needs. We could better describe the existing condition of the landscape across all ownerships, present a more clear picture of forest restoration needs, and identify the areas of highest need. In one look that people could argue about the details or argue about the priorities, but at least be presented with a holistic picture of the forest. So here's the project objectives. We're going to build an all-land stand layer that uses existing data sets, can be applied to all forests regardless of ownerships, can be updated easily as new data become available, and summarizes important information at an appropriate scale. So that's what we're going for. So first step here is to acquire and organize the data sets that will feed into this picture of Minnesota's forests. So on the right, you can see the project structure in files and geodatabases. Here, you'll take the raw data sets just as they are publicly available, wherever you get them from, and you'll just plug them right in there. And then you'll run a workflow that puts all these data sets into intermediate projects and finally comes out with a seamless stand layer. So we take stand inventory from everywhere we can get it, Fed, state, county, tribal, private. Then where we don't have good inventory data or it's too old, we take ecological boundaries from the National Wetlands Inventory or the soil surveys where it exists. We take ownership layers, the tax parcels, and we match it against something that's more comprehensive, and with the GAP project they did in 2008. We look at vertical structure, and to the extent that we have it, whether that's hopefully coming from the new LiDAR products that are really exciting, the high-density LiDAR initiatives most of you know about. But in the case of the absence, we still have fairly recent, useful, comprehensive view of the vertical structure from 2006 to 2012, the state LiDAR. And the Nature Conservancy funded Mike Falkowski to rerun the metrics using across the state wherever that occurred in order to support this project. So we had consistent definitions and parameters to make the comparisons across the state. So that gives us canopy heights, cover, and density at a certain time period, but a fairly recent time period. And then bringing disturbances. We have the Resource Assessment Shop does disturbance change detection. We have our planning data, whether it's from FACTS or the DNR's 5-year plan data, and bring this all together. Oh, and then we bring in remotely sensed cover types, land fire, national land cover, some of the early discussional forest products that Mark Nelson and James Garner have worked on, native plant community predictive mapping, time series analysis. So you can basically see how almost everyone in this room is working or related to the data that is trying to be compiled in this project. So then we build a workflow, and the workflow that I built for this uses model builders. I'm a very poor Python programmer. I've got basic skills, but not great skills. Model builder is really great because it provides a visual framework to how all these data sets are interlocking. And we can convert it to Python for those that are more technical and want to take aspects of that and pull it apart. So you take the raw data sets, you organize them, then you leverage the different information that is all coincident there, but maybe in different conditions, and basically within any parcel, you take the best overlapping data. So that the seamless map is built of data sets in all different conditions, but you have the best descriptions of the cover types, or at least a range of data available to you, so that you can look at a stand and say, all right, it may be a county parcel. It was drawn in 1995, and here's what they said was there. We know that there was a disturbance in this part of it in 2015. And we know that, according to the most recent LiDAR data, that the structure is in a mixed class, so we can say something in one area about the quality of the underlying data that's there and have that all in a single glance. So here's an example of some of the processes that run in these submodels to create this seamless all-in stand layer. So here we've got I just put in 2 layers. I put in the forest service, sand inventory, and the state. And you can see that it's hard to use these because they don't overlap. Who do you clip it to? I don't know. Or I'm sorry, they do overlap, and they overlap in strange ways across the landscape. So one of the submodels will do a generalization. The generalization tends to rasterize these at a 20 meter by 20 meter pixel scale. And then once all these layers are bumped together and the decision matrix is made about what information you keep and what you leave, you get rougher but polygon information that captures the essential geographic information that you need there. So now you're building something that's seamless, and you're only moving these pixels typically within a 20 meter pixel. Now maybe for stand inventory or for some of the wildlife habitat issues that you're looking at, you need something that's more detailed than this. But when you're trying to come up with a project that crosses ownerships, moving the boundaries by 20 meters is not substantial at all. You just want your single look. And if it's slightly rough, well, it's not going to bother you too much. So I think another example of a submodel that we'll run here is where we don't have inventory data, good inventory data, where we have older ecological boundaries drawn. We may have to resort to LiDARs to draw stand boundaries. So this is poor, but works better than nothing when you're trying to do something seamless. So you've got a submodel that looks at whatever the underlying rails are and then develops stands to fill the gaps where we don't have inventory data. Disturbances. We've got a lot of good products that have been produced about early successional forests. Mark Nelson worked on this one. This one used national land cover types, but then went and put in disturbance in 5-year increments. Well, one of the advantages of having all this data available at your disposal is that you can continue to take these old finished data sets but add to them. So I've got all the disturbance layer at my disposal. I could look at the next 15 years of disturbance. So this landed in 2009. Well, I could say, based on what I know from Forest Service, based on what I know from resource assessment, I can now put parcels in to say this is the next 5 years of disturbance, and then 5 years after that. And even with planning data, I could say up to 2024, this is the state of the forest. So this is the workflow advantages. It's adaptive. We can revise and adjust as necessary. We can rerun it as updated data becomes available. That's crucial. I don't see this as ever a final product. It's something that gets updated probably yearly with whatever new data we have. And we can incorporate new data sets and useful metrics. So the major products here are a seamless all-in stand layer, and then report tables and graphs for any project area. So once you have a seamless stand layer, you say, I want to report on sub-watersheds, I want to report on counties, whatever. Just run that through, and you could have a lot of the reports that you need on the data that's there, broken down by ownership, interactive pivot tables, just built right into any run that you want to do on the most recently available data. So before I show, originally I intended to drive you through the map because it's really cool when you can see stand inventory polygons across all of Minnesota and just go wherever you want, but I'm stuck with a PowerPoint. So before I show screenshots of the stand layer, I want to address this question. When you think of stand inventory data set, what does a stand inventory data set do? And at its most basic conceptual level, a stand inventory data set is about data relationships. It's about when a person or forester comes and draws those boundaries, they're saying, this is an incredibly complex landscape we're looking at, but I'm interested in these parameters and the relationships between these parameters, and I'm going to bind them and summarize them across these parcels. So understanding that informs a lot of where we make the decisions on how the priority of where you draw stands where no human has drawn them, how you make that decision. And then who are the intended users? Well, I see a range of intended users for this. Everyone from anyone that uses the stand inventory data layer right now to make decisions, whether that's expanding up to try and describe the existing conditions of the forest, or scaling down to come up with a project area, whether you're the DNR or the Forest Service, or any agency, any collaborative. It's pretty much anyone who needs stand inventory where they currently struggle to use it. So this uses ArcGIS Pro Model Builder. All input data sets are generalized to 20 by 20 meter pixels during the intermediate processes. The minimum stand acre size is 1 acre. There's a lot of reasons for that polygon, that size. Mainly that our landscape is incredibly complex, and when you started with we don't have high density LiDAR everywhere, so given some of the rough data that we had, going too large meant that a lot of useful ecological information was ruled out. However, 1 acre is not something foresters like to use. They want stands that are larger. With a minimum unit size of down to 1 acre, you can build up whatever you want, but you can't scale it back down. And then here's the priority we use for our stand boundary generation. Ownership layer, supreme, once each of these have to be refined independently. Then stand inventory, then ecological mapping, then LiDAR with recent disturbances, and then Landsat cover products. So this is the question of how do you draw the boundaries. There's a lot of minutia about lots of problems that you encounter within each of these subgroups, but that gets sorted out in the model. So then we have an all-land stand layer, a seamless polygon layer that contains all this data in one layer. Process data, the Forest Department. Right now it's 1.4 million polygons, and one of the advantages of coarsifying all these curves is that when you're losing the 20 meter pixel resolution, the layer gets usable and simplified pretty effectively so that you don't have a ton of loading problems. So this is stand information across all ownerships in Minnesota. Cover types based on land fire, national land cover definitions, national wetland definitions, lots of other useful parameters summarized for each stand. Vertical structure based on the LiDAR data. That's the old LiDAR data that's as recent as 2012. But if you have a forest that is not either young and changing rapidly or in the old and transitioning rapidly, for stands that are somewhere in the middle, that LiDAR data is really useful still today for describing vertical structure. Grouped by height, cover percentage, other metrics. You have age since disturbance. You have information necessary for project planning reports. And you have it all in a seamless layer. So so I'm going to just show you images about different visualizations of a single layer so I can kind of capture where we're going with this. So these are just the polygons similar to what I showed you earlier, Forest Service in green, state in pink, other types maybe based on other LiDAR or ecological boundaries from National Wetlands Inventory in white. Because of the intended users and where I think the value of this is really going to be, maintaining the inventory data, a lot of the core data that comes from the inventory data, and making it bridge to agency use is essential to making this usable. So this product keeps crucial underlying data of each stand, whether that came from tribes, county, state, or federal. You have the stand ID key, whatever it was used, kept for every single stand. So, and the rough geometry is preserved. It may not be exactly aligned, but you can make queries across the landscape and then take the subset that belongs to the DNR and say, okay, join those with some information to the DNR. So you have this back and forth that resource specialists really need. So we could look at ownership definitions, wherever they exist, age, class definitions. These are 10-year groups. And a bunch of different cover definitions. This is based on majority land cover database. Or the land fires forest types. And these are, anyone who's used these coarse these coarse raster products knows that these definitions aren't always accurate. But when you're given a stand and you could see, oh, this was inventoried in 2018, and here's what Landsat thought about it, but here's what someone said on the ground, and compare those. Well, you know what information to pull from. But when you're given a stand that was inventoried in 1990, having all that information on a single stand helps you describe what is going on in that stand when the information collected wasn't recent. So that's why all this having in one place is helpful for decision making. Recent disturbances, we brought it back to 1990 with some products we're hoping to add. We're hoping we can get a good picture of disturbance back to 1974 with the early Landsats change over time and time series products. National land cover predictive models, the red is fire dependent, green is mesic hardwood. And then tree canopy metrics from the LiDAR data. So now we have all the metrics at your disposal describing the vertical structure, whether it's max height per stand. And there's a lot of different ways that you can slice this and get good information in it. Whether you take, okay, what is the max height across this whole stand? Or you also, one of the things these polygons do is they will tell you within the stand, 90% is trees and 10% is non-trees. So then you can get the canopy heights on just the trees. Because we have to consolidate stands to some degree, you will have information that says this is 50% trees combined in the stand and 50% non-trees, so that you can get canopy heights on just the trees in that stand, understanding that it's sparsely or clumped in a way. More LiDAR data. Here's the mean canopy height, or close to median canopy height. So some metrics we've already included. Within each stand, you have percent conifer versus deciduous or tall trees. But then now you can build queries across the landscape and connect it right back to the ownerships that you need to contact or figure out how to do management for. So you can run queries for landscape metrics back to patch dynamics. Give me all forests with this percent cover in this age class by acres, mature patches, openings, or wetlands. Give me the report within our project area, if it's a collaborative project area. You could query for the connectivity of specified habitat structure relationships. You could come up with a coarse way to do available timber estimates from veg density. And the other added part is what we're hoping to build off from this is come up with restoration and resilience priorities within these stands, within this data that's there. So anything that's of management significance, if there's sites of biodiversity, sites of wildlife importance, like that will all be within a single stand layer. And then the Nature Conservancy has been working really hard on taking this as kind of their framework and then overlaying a lot of these restoration or resilience data layers to basically say, where does this stand fall into the larger landscape about what its restoration priority might be across an adjacent area or within a collaborative. And hopefully that will lend itself to all these different stakeholders coming with a more comprehensive picture on what the existing condition is, and then also what is the priority here for how we do our work. So Andrea's sitting right here. Do you want to speak on that at all, or address any of that?
Sure. Yeah, I'll just add two things. So the Nature Conservancy, we're really excited for this really excited for this product, and just see it.
Close the mic. Sorry, watch out for the cord though.
We see this as a really useful tool to really get to the place where we're doing integrated landscape scale planning, where we're using some of the existing stand inventory data along with ecological boundaries to start to map things out and have that wall-to-wall across the entire state stand data layer that we can use for planning. There's two items that I'll add, and one is that we hope to be a contributor to this product as well as a user of this product. And as a contributor, we've been working closely with the Natural Resources Research Institute, particularly John DePlissis and George Host, in trying to use the LiDAR data along with FIA data to develop a new data set that will look at sub-canopy forest structural complexity. So this is something that we're still in the works on, trying to figure out, but we hope that within the next 2 to 3 months we'll have a product that we can share, and that will then be added into the all lands stand data layer. And then as a user, as Chris had suggested, that we're also looking at developing a restoration needs-based assessment where we can use the polygons generated of the stands across the state as a base foundation, and then develop out a set of restoration need classes as well as desired future condition classes that are based on native plant community data, to really start to define where are and how are some of those restoration needs across the state that then could be used by land managers to help prioritize actions. So that's all I'll share. We're just really excited to be a part of this project and feel it's a real privilege to be working with Chris and Mark Nelson and George Host and so many others on this effort. Thanks.
Yeah, it's been a good wonky effort for all the state nerds. We've really appreciated going to town on it. So I've got one more slide and then I'll take questions. So the concept here is filling the gap between large core scale data sets and ownership specific site data. This is the best available data approach. It is bumping all these data sets together, but this is not a new initiative. It requires all these data sets that are already existing. Obviously, a lot of our data is not great, but this helps improve what we have. However, the great news is that because it's a workflow, the product's improved as the underlying data improves. It doesn't divert from other ongoing initiatives. We can continue to add whatever new thing comes down the pipeline into this framework. And then it also organizes data sets from multiple stakeholders. And then, as Andrea said, we are looking at the latest version and revising internally, and we're hoping to share with interested parties by summer this year. All right, so any questions?
We'll take one quick question because we're just about out of time.
Where will this be available through this summer?
That's a really good question. I don't think we have an answer to that. It may be you email me and say, hey, let's share this.
We do want to have a publicly facing web page. We've been discussing potentially conservation gateway as an option, but I think that's yet to be fully determined. So I would say stay tuned, but we want it to be a publicly facing page that everyone can access.
And there may end up having to be two versions of this. It depends. Since this brings in so many different data sets, most people are totally comfortable with it's publicly available, some are not. So we may have a strict version if people are like, well, you can use this in a small way, but not a large way. I'm thinking that's going to be a significant number of people. So thank you.
Okay, thanks, Chris.